Okay, this is a. What's the difference between oxidative and workup oxidative?
Reductive makes all.
Yeah, reductive makes alcohol. So this is the reductive.
Product for the oxidative.
Do you mind sending me those flashcards from
Oh, yeah.
All right, I hope you guys didn't have a hard time getting down here today. The ice advisory ended at 10, though, so we all should have been fine for a noon class, right? I got up, schools are canceled. My kids were like, I dressed, I came to work. They're like, where are you going? Like, like the whole world was shut down. I'm like, yeah, we live in the real world, kids. They're home watching reruns of Modern Family. That is like their current obsession. So I haven't seen it at all. I get it, though. I get the program a little bit, but I don't watch much TV. Anyway, not that you need to know what they're doing. All right, there's a handout today. I'm like, why am I telling them this? I have no idea. Okay, it's two-sided. One side should have NMR, and one side will have like some substitution elimination chemistry on it. Okay, so if you don't have the handout, make sure you find Kim. She's sitting in the back here by the door to get the handout. So if you don't have the handout, maybe raise your hand. She can come give you one. I think we need a couple handouts up here. She's coming. Okay. In the meantime, a couple reminders. One, we start clicking on Friday, right? So you need to purchase a clicker. Either Responsive Innovations, those are the older models, or Turning Technologies, those are the newer models of clickers I've come to understand. They need to be registered by tomorrow night at 11. I got an email this term that tells me the systems are all updating at 11 now instead of 12. So I don't know if that's true, so let's just be careful and do it by 11 if you want to be able to click on Friday. I'll put the points online right away. So if you get anything above 0, it means your clicker worked. Okay, but if you get a 0, right, or you get no score, that means something's wrong with your clicker, or you don't know how to click, or something. So you need to kind of fix that problem, and I'll help you fix it. Okay. The second thing is the homework. The homework is released right after class. So once I go back, I forgot my lunch, so I have to go get lunch. And I know you're learning more about me than you really need to know. So I'm going to go to lunch, and then I'm going to go back to my office, and then I'll upload the homework. So you'll get that from your homework 1 folder online. Everybody has the same homework. You're going to think that it's a little challenging. I know you will. I know you're going to complain about it. This is a homework, so you have more time. This is not a test, right? I wouldn't do something like this crazy homework on a test. That's a lot. But there's a lot of spectra on there because you're still questioning your spectral stuff, and I'm trying to get you to own up and learn it. Okay? So you either own up and learn it, or you copy it from a friend. I mean, I'm going to have no idea, right? So do what you may with that. We only hand in the answer sheets. We can make a pile right here by the stairs on Friday, right at the beginning of class. Okay? That's all my administrative stuff. Are there any questions before we begin? Okay, so we're going to start with the NMR side, okay? There's no IR or any other data, just sort of for simplicity. You don't really need it, actually, to solve the problems, believe it or not. The formula are given above each spectra. There's 3 of them, okay? They're all benzenes, and I brought it because, first, people were talking to me about still wanting to do NMR, and second, people were questioning me about how to put substitutions on benzene, and this actually will help in the lab. There's some lab problems like this, too, okay? So they're all benzenes. Now, if you don't know they're benzenes, one thing you could do is write out or calculate their degrees of unsaturation, or IHD. You'll find that they all have more than 4 IHD. And more than 4 IHD is definitely benzene. Benzene is definitely 4 itself, right? Because benzene is a ring with 3 double bonds in it. So benzene accounts for 4 IHD, 1 for the ring and 1 for each of the double bonds. Okay? So if you have 4 IHD or more, the most simplistic solution is that there's a benzene in there. If you are not sure, you can look in your NMR. Your NMR should have peaks between 6 and 8 parts per million. That's the aromatic region. So there's corroboration. You have more than 4 IHD, and then you have peaks in the 6 to 8 parts per million region. Okay? Now, those peaks in 6 to 8, right, generally have a variety of shapes to them, multiplicities, and overlaps, and that sort of thing. But in general, they're corralled together, and you'll be told how many protons there are that are aromatic in total. Or you might see them in a bunch of smaller numbers, and you add them up in total. But generally, you'll be able to total this region to either 5H, which we've said is a monosubstituted benzene, right? That means that the benzene still has 5 protons on it, and then it's got something else offshoot from it, right? Off of the benzene. So if you see 5 total aromatics, it's what we say a monosubstituted benzene. Okay? Doesn't matter where you put that, it would still all be a monosubstituted benzene. Meaning I put my substitution off of carbon. That would be on a clock 2 p.m., right? It could be 4 or 6 or 8. It doesn't matter. matter, it's all monosubstituted, okay? If you come to 6 to 8 and you total now 4H, you have a disubstituted system, okay? Now, there are 3 potential ways you can have a disubstituted system. There's only one that you're responsible for. So the one that you're responsible for is one that looks like this. If you have something like 2 doublets in here that say 4H, this disubstituted system actually is a 1,4 system. There are 4 remaining protons on your benzene, but they're substituted. The benzene itself is substituted 1,4. Okay? We call that para substitution. That lends itself to this pattern. Any other pattern means there's 2 potential answers, right? Any other pattern with 4H there means that it can either be 1,2, right? Or it could be 1,3. You are not going to lose points, right? This little squiggly is just a substitution, right? You won't lose points for putting down a 1,2 substituted system or a 1,3 substituted system. Neither will be marked wrong, okay? Do you understand what I mean? There's no wrong about it. If it's not this pattern and it's 4H of some other pattern, it does not look like this. It's either this or this. Doesn't matter, you choose, you'll both be marked right. You and your friend chose 2 different things, okay? And then there's, if you have 3H, I hope it makes sense then that you have a tri-substituted ring, etc. Does everyone understand what I mean with this short little logical piece? Yeah?
So if it's a doublet and between 6, 8, and 4, 8, then we can definitely parasubstitute?
Yeah, so parasubstituted will be like 2 doublets, okay? Can everyone see on this handout, there should be one that is parasubstituted. Is it the top, the middle, or the bottom? The middle, okay. So the top one, is it this or this? Either, that's right. So the top one is either, okay? And the bottom one is clearly a tri-substituted. And again, it doesn't matter how you tri-substitute it. You can do 1, 2, 3 or 1, 3, 4. It doesn't matter, okay? Does everyone understand what I mean by that? Okay, so let's take one of them and solve it. I'm going to choose the middle one, okay, the parasubstituted one. So we know we have a parasubstituted benzene. Like I said, you try and make some guesses before you get into the NMR. You want to have some logic about it before you jump in and try and start looking at it. One thing I would look for if I were benzene is it parasubstituted? Is it 1,4? If I see that pattern, then I automatically have some really good information, okay? Past that, the other thing that's going to help me is degrees of unsaturation, right? So I'm going to calculate the degrees of unsaturation for that molecule. So it says that I have 11 carbons, so 11 times 2 is 22, minus the number of hydrogens plus halogens, so that's 14. So this gives me 8, plus the number of nitrogens, that's 0, plus 2, in total that's 10. 1/2 of 10 is 5 IHD. You can memorize this formula if you want. You don't have to. We'll put it on the board if you ask for it. No problem. Okay? But you have 5 IHD. 4 of them have been taken up with a benzene, right? We know that. 4 are gone. So I have 1 IHD left. So I take a scan of my spectrum, and I have no idea, right? I'm like, makes sense that, though, it would likely be a carbonyl. I'm going to guess a carbonyl because I have all those oxygens, right? I have 3 oxygens. So logic tells me my 5th IHD is likely a carbonyl and not a CC double bond because I don't have, that many places to put oxygens, right? So I've got to have to think about how to utilize some of those oxygens, okay? So now I come back and I'm going to go and work through the spectrum like we've done before, okay? And I'm just going to kind of sketch it out as we go here. So it looks like I have 2 separate 3H shifts, right? Unique environments. And I can sort of see that they're each triplets. I hope you see that. That's at about, I'm going to say, 1.1 and 1.2 parts per million, okay? There seems to be 2 things there, right? Each of them are integrating to 3H, right? They're pretty far upfield, so they're not next to an oxygen or a carbonyl or a ring, right? And they're each triplets. So they each have 2 hydrogens on the neighboring carbons, each of them, 2 hydrogens on the neighboring carbons. So in essence, I have 2 ethyl fragments. This is the chemical shift that we're looking at right now, and they're each next to a CH2, okay? They're each next to a CH2. Again, I get a methyl group from the integration. The fact that it says 3H there tells me it's a methyl. Its multiplicity, which they look like overlapping triplets, the expansion sort of helps me see that. Okay, they're split into 3. 3 minus 1 is 2. 2 protons on the neighboring carbon. So there are 2 ethyl fragments there. Okay. I come up and I look and I see in the 4, a little over 4 region, I've got something at 4 and probably something at 4.3, roughly. Okay, and they're each 2H. They're methylenes, right? So they're CH2s. Each of those are CH2s. Well, they've got to be these CH2s, right? I'm going back and I'm saying, does that make sense that I have CH2s? Yep, I do. I thought I had them before, so I'm good. And I look at them and they're each quartets. That's even better, right? Because now I know that they are these CH2s, right? They're next to the CH3s. Because when I have 3 protons in the neighboring carbon, 3 plus 1 would be 4. They expect a quartet out of that, right? But their placement in the spectrum tells me that they're likely next to these oxygens, right? Because of where they are. They're up by 4, right? So that's telling me they're next to these electronegative atoms. So I'm going to now sort of expand this and say that I have OCH2 CH3s here, okay? And this is indeed what it is. So now I have everything I need except for 1 carbon, which I've made a guess is this carbonyl. And truth be told, that is exactly what this molecule is. If I put together all of my evidence, I have a 1,4 disubstituted system. I have 2 ethoxy fragments here, right? Ethyls attached through an oxygen to the main chain. So 2 ethoxy fragments here, and a carbonyl that I'm kind of guessing to use up my 5th IHD, right? And the fact that I had 3 oxygens, I have to use up an oxygen and an IHD. It makes sense that it's a carbonyl. So when I put all of that together, I would simply say, okay, I'm going to sandwich the carbonyl on one of these, and I'm going to just keep that ethoxy on the other. And this is the structure that gives rise to that middle spectrum. Okay? So there's 2 more structures here that you can solve. So by all means, I will put up the answers to this. I haven't deposited the answers to problems 1 to 8 yet because Kim's still using them in discussion. But if you're someone who wants the answers, they're posted on my door. There's actually the answers right there, 1 to 8. It's what will be posted online as of tomorrow after discussion. It's on my door. So if you have done all the problems, you can run by my door and check all of your answers, or you could just wait till tomorrow afternoon and you can check your answers then. Either is fine. Okay, and I'll post the answers to these. I'll make an addendum at the bottom that says, you know, February 5th handout, top spectrum, middle spectrum, bottom spectrum. Okay? There are questions about that? Yeah? The 3 H's look like a quartet, but what are they? Oh, together look like they're actually 2 triplets. Yeah. It might be helpful if I put this, when you print it, you know, it loses resolution. I don't have the best printer in my office. That's your Maryland tax dollar at work. But I can put up the actual document online. It's easier to see on the actual document. Okay? Yeah?
What on an NMR would show you that there'd be an alcohol? Because when I saw those 3 oxygens,
Okay, that actually brings up a really good point. What would symbolize an alcohol would be something like, and everybody, make sure you have your handed out, the bottom spectrum, that peak that's between 4 and 5. This actual textbook that I scarfed this problem from is not a textbook that says exchangeable. It's just not one of the things they do, because you don't have to do that, right? But that proton is exchangeable between 4 and 5. So my answer to you is, when I see a singlet, right? A singlet, somewhere in the spectrum, 1H singlet, and it says exchangeable, that's either an OH or an NH, okay? So you'll either have an OH or an NH. You shouldn't have both. So you'll have an OH or an NH, and you get that probably from the formula, right? Does that make sense? Okay, yeah? Oh, the exchangeable will definitely be on an exam. I actually meant to do it, and then I was copy happy, and I printed it, I ran down and copied it before I put it on there. And I wasn't about to sit on 200 handouts and write exchangeable, exchangeable, exchangeable. And I didn't want to ruin another tree either. Yeah?
Do the H's on an OH or an NH go by the chemical formula?
No. You never see splitting to a hydrogen that's on an oxygen or a nitrogen. You can't actually do that. The reason that it's exchangeable is because the proton's not on the molecule all the time. Sometimes it's with the solvent molecule. So sometimes it's on the solvent, and sometimes it's on the molecule you're taking the NMR of. If it's not there all the time, it can't actually split anything. And that's why. And that's also why it's exchangeable. If you want to hear more about that, you can come into the office. I'll give you a whole line on that. Yeah?
Can you clarify on exchangeable again?
So exchangeable means, it literally means that it's, okay, like an alcohol, right? So if I look at an alcohol, and an alcohol is in water, there's some acid-base chemistry that happens here, right? That water can pull off that proton, right? So sometimes it's on and sometimes it's off. There's acid-base chemistry that's happening there all the time. And that's actually what it means. Sometimes it's on and sometimes it's off. Okay? Okay, great. So today on our, next thing, that's right. So next in review, people were asking questions about the alkyne mechanisms, which I guess you didn't get a lot of time with alkynes either, just like NMR, so it's really making me sweat. So let's talk about those alkyne mechanisms very quickly and briefly before we get on to substitution elimination. Okay, so first and foremost, there's a difference between terminal alkynes and internal alkynes. I just put two alkynes on the board there. The top one is a terminal alkyne, and the bottom one is an internal alkyne, okay? So terminal and internal, all right? Different chemistry with the terminal alkynes compared to the internal alkynes, okay? First and foremost, with the terminal alkyne, I can deprotonate this, right? Does everyone remember that you can deprotonate this? You can add sodium amide, so NaNH2, and that creates now for me an acetylide, right? Or a version of an acetylide ion, which means I've pulled the proton and that electron pair is sitting in an sp hybridized orbital. It's a nucleophile, right? And you learned that this could actually do SN2 type chemistry, right? You can actually make substitutions off of a terminal alkyne. I can add, say, ethyl bromide and show an SN2 reaction happening here to get now a larger backbone, right? There's two ways in Organics 1 that you learn to expand your backbone, to make a larger backbone. One is to have a terminal alkyne that you deprotonate and run an SN2 reaction with. Okay, that's what I'm showing here. That's the review of alkynes. Does anyone remember the other way that you can grow your backbone? An epoxide. That's exactly right. If I take an epoxide and I open it with a Grignard, that's the other way, and this is a big hint. Yeah, big hint. There's a good thing to know, all right? If I take an alkyne and I make an epoxide from this, I can add a Grignard, right? I can add a Grignard. And the Grignard can be anything, right? I can have, it's given the classification RMGBR, which really means it's a carbon nucleophile. Yeah. So this is an alkene, yep, that I can make an epoxide from. Here we can use MCPBA, or we can use a peroxy acid. This was on our chart from last class. So I can make an epoxide, and with the epoxide I can do a ring opening with a Grignard, right? This is a Grignard, RMGBR. It's a carbon nucleophile. And remember, you can make lots of different Grignards. You can have this type of Grignard. I pause for reflection. I can have this type of Grignard. And I can have this type of Grignard, right? Showing that they can be off of sp3 carbons or sp2 carbons, right? In essence, this is my nucleophilic carbon, the one the magnesium is attached to. This is my nucleophilic carbon. Does everyone see what I mean? And you can open your rings here, always on the less substituted side, right? Always on the less substituted side. So this gave me now a chain expansion, right? I result in an alcohol that I can go do other things with. So I diverge to remind you that one thing we could do with alkynes was do chain expansion, okay? But that chain expansion can also be done with an epoxide, okay? So there's two ways you learned about chain expansion in 231, okay? So backtrack to the terminal alkyne, which I wanted to review for you very quickly. There were two reactions that you learned that were hydration reactions. And so I'm going to come back to this internal alkyne in a minute. So from this terminal alkyne, I could do two different types of hydration reactions that look very similar to the hydration reactions from alkenes. One was to take water, and I would need both a mercuric catalyst, a catalyst that's mercury, and acid. With an alkene, right, you had H2O and H2SO4 alone, right, and that added OH. But in this case, with the terminal alkyne, you need mercury as well to catalyze the reaction, okay? I could show the mechanism. I'm not going to. If you want to see it, you certainly can come into the office. I'm happy to do them, okay? But in terms of this chemistry that happens, you know the OH in this reaction always winds up on the more substituted side, right, of the pi bond that reacts. The more substituted side means it's here. And this is a very special type of alkene, right? It's what we call an enol, right? An enol is given to an alkene that has the OH directly on a vinylic carbon, an sp2 carbon. This carbon that I'm pointing to right now that the OH is on is called a vinylic, like vinyl records. Vinylic is how we'd say a carbon. It's the actual sp2 carbon. That enol is given a special name when it's off these sp2 carbons. We call them enols. And enols tautomerize. This is one of the mechanisms we learned this semester in organic. We learn about tautomerization, but so we're not going to show the mechanism. But what happens is the double bond moves to be a CO double bond, and the hydrogen moves over to the tail end. So what I get from this is this molecule here. This is the keto version of that enol. Okay? So again, the double bond moves to be a CO double bond, and the hydrogen moves to the carbon that lost the bond. We'll be showing this mechanism once we learn something about how these mechanisms run. But this is tautomerization. Everyone notice that this is a ketone that we get out. R, C double bond O, R, ketone. If I run other mechanism that's called DSB, DSB stands for dicyamylborane. I'll write that out. Dicyamylborane. And that looks a lot like BH3. This is BH3. This is dicyamylborane. See how they each have this BH bond that's donated in that first step to react with the pi bond? So the top one is dicyamylborane. It looks a little bit like a reindeer, right? You never need to regurgitate this structure for me. Ever, ever, ever. My point is that it acts like BH3. And BH3 is anti-Markovnikov, right? It adds an OH on the less substituted side. So the enol that I get out of that is this enol. This is specifically the enol that comes from the reaction of DSB followed by oxidation with H2O2, OH minus, H2O. Okay? This enol will tautomerize to give me an aldehyde, right? If I do the same thing that I learned, the double bond becomes a CO double bond, and the hydrogen moves over to here. This is the molecule that I get, and this is an aldehyde, right? R, C double bond O, H. Everyone see that? Okay? So these hydration reactions with alkynes gave me two different products if they're terminal. Now, an internal alkyne isn't going to give me two different products at all. And we can think through that logically, right? So if I look at my internal alkyne, and I use the DSB, etc., or I use the H2O with my catalyst, it doesn't matter. There's no more or less substituted side, right? There's no more or less substituted side. There's no ability to say Markovnikov or anti-Markovnikov, right? Can't do it. There's equal substitution. So each of them are going to lead to an enol that will tautomerize to give me a ketone. Both of them, okay? So in this case, my ketone is 2-butanol, all right? Does everyone see that? What I mean about the difference between a terminal, giving me an aldehyde with one condition, and a ketone with the other, and an internal, okay? This is really the main selling point. This is the chemistry chemistry that we need coming into orgo 2. Okay? If for any reason you want to go over these mechanisms, that's totally fine. I cannot devote class time, though, to the mechanisms themselves. So, because you're supposed to learn them last time. So if you need help with that, come on into the office. I will write them out for you. I will talk you through them. Okay? Or look in your book, or whatever you need to do. Yeah?
And your arrows here, does that mean that it's the product is favored more towards the...
Yes.
Okay.
For keto-enol tautomerization, the keto and aldehyde versions are always favored. A CO double bond is actually stronger than a CC double bond. Okay? So in the tautomerization process, the ketone and the aldehyde are favored. Okay? All right. So today we're supposed to be talking about substitution elimination chemistry. Okay? Now, online already is a flowchart for substitution elimination chemistry. It's already online. You can go get it. It is a decision tree, basically, that helps you decide whether or not conditions that I'm given are going to run SN2, SN1, E1, or E2. Okay? So I'm going to review for you what you need to be thinking about when you look at that. Okay? First thing you need is what I would call an alpha carbon, or a carbon that has a leaving group attached. When you started substitution elimination chemistry, you started with halogens, right? Alkyl halides. So we can look at an alkyl halide. So here is an alkyl halide. And I would call this, my terminology is I would call that the alpha site. The carbon the halogen is attached to, or the leaving group is attached to, right? That was what you were looking for. You were looking for a molecule. When you scanned the molecule, you would say, okay, is there an alkene here or a pi bond? Because I might be thinking about doing an EAR reaction, right? Or do I have a halogen attached? Because then I would be thinking about doing some sort of substitution elimination chemistry, right? Those are the things that you learned about in Orgo 1. So the first thing you need to do is classify this alpha site. Now you classify them 3 ways. You classify them as primary, secondary, or tertiary. What is this alpha site? Primary, secondary, or tertiary?
Secondary.
Secondary. Great. So 2 carbons attached to the alpha site means that it's secondary. We need to be able to classify a little bit beyond that. And this is where chapter 17 comes in, right? So you're going to go and you're going to fold in chapter 17 as we continue to talk about these things. Chapter 17 is going to introduce 2 new sort of classifications. The first classification is the benzylic classification. So this here is a benzylic site, okay? A benzylic site, as it's classified, is because it's once removed from the benzene ring. The very next carbon is part of the benzene ring. So we call any of those sites that are once removed from the benzene ring, we call them benzylic. Okay? That's just an additional classification. Now it's important because with the benzylic classification comes the ability to have resonance stabilization. Okay? This site here, I would classify as a primary benzylic site. A primary benzylic site. So it would have a double classification. I would not only say it's primary, secondary, or tertiary, I would also say if it's benzylic or allylic, and I'll show you allylic here in a minute. So an example of a tertiary benzylic is, say, this guy here. This is now a tertiary benzylic site, the one that I've just drawn up here. Okay? Now, benzylic sites, again, are important because they come with them resonance stabilization. All right? If I think about the potential for that primary, which you would never say, a primary site, you would never say would undergo SN1 or E1 type stereochemistry or chemistry, because it doesn't have a very good carbocation. This primary benzylic does, right? If I think about that primary benzylic site and I lose the Cl to create a carbocation, this carbocation is indeed resonance stabilized, right? There are 4 other resonance structures I can draw for this alone. So in total, 5 resonance structures that I can draw. You should be able to draw all of them and come up with a resonance hybrid that looks like this. Okay? So if you can't do that, that's something you want to be able to go practice, resonance. You should be able to come up with a resonance hybrid that looks like this, which in essence is saying that positive charge is not localized on that benzylic carbon alone, right? It's actually shared by 4 carbons. That electron density is spread out in the structure, and this carbocation is actually very stable. Much more stable than a regular old primary carbocation, right? So classifying it as primary alone isn't good, okay? The second one that we fold in at this point is something called the allylic site. This here is an allylic site, okay? That's an allylic site. An allylic site is a carbon that's once removed from an alkene, right? The direct next door carbon is vinylic. It's part of the alkene. This is what I would call an allylic site, and I would classify it with that double classification. In this case, this is primary allylic, okay? Primary allylic, all right? So, again, we know that it brings with it, the fact that it's allylic, some great stabilization. If you go and look at it, and you put that positive charge by losing your leaving group, right? You know that you have another resonance structure here, right? And that charge then is shared by both of them, and you would get a resonance hybrid, right, that looked like this, indicating the charge is being shared by 2 carbons, bringing with it resonance stabilization. Awesome, okay? So we need to be on the lookout for these allylic and benzylic sites. So always classify the alpha site, primary, secondary, tertiary, but then if necessary, give it its secondary categorization as allylic or benzylic. Only sometimes, right? Not all the time. It's just not possible. Okay? So where does this come in? This comes in the following way. SN2 mechanisms, right? SN2 mechanisms. Tell me something about SN2 mechanisms. What do you know about them? What did you say? It's concerted. Okay, great. It's a one-step or a concerted reaction, a one-stepper. Okay. What type of alpha sites does an SN2 reaction prefer?
Primary.
Primary. Why?
It's faster.
Because it's less sterics, right? Less crowded. So this definitely prefers less crowded sites. Okay? And we know that it prefers moderate nucleophiles. We'll be talking about that. But for sure, we know that one of the main things about SN2 is that we don't have crowded alpha sites. Yeah?
Why did you get a hybrid shift with the other
Hydride shift, meaning here.
Yeah.
Because then that would lead to a vinylic carbocation if you did that. And vinylic carbocations are terrible. Terrible, terrible. This is an sp hybridized carbocation. An sp hybridized carbocation, sp is more electronegative than sp2, so that's bad. Never ever hydride shift to vinylic. It's a good question though. It's a common question. Okay. So back over to here, we say SN2 not crowded. So adding this classification of benzylic or allylic isn't really doing anything to the crowdedness, right, of these sites. Really all that matters for SN2 is it primary? Is there one thing on there? Secondary or tertiary? That's all that matters to SN2. But to SN1 and E1, we have added a whole bunch of things that it will undergo. Because SN1 proceeds through what type of intermediate? Carbocation. So it was all about carbocation stability, right? SN1 and E1 was all about carbocation stability. So I'm about to put up your carbocation stability chart, including these new allylics and benzylics. Okay? So you knew, in terms of stability, so we'll go increasing stability as I move from left to right. So we would say more stable as I move from left to right. Okay? You start down here with your vanillic carbocations. Those are always the least stable, right? You come next to your methyl carbocations. Okay? Pretty unstable, right? Never really liked methyl carbocations. We come next to our primary carbocations. Primary. Note, only classified as primary. Not primary allylic or benzylic. Okay? Next along this continuum is secondary carbocations, followed now by primary allylics and primary benzylics. Primary allylics and benzylics are more stable than secondary carbocations alone. What?
You mean that they are more stable than tertiary carbocations?
No. Primary allylics and benzylics are more stable than secondary. Primary allylics and benzylics are more stable than secondary. I keep going along my path, I get to tertiary carbocations, and then comes secondary allylics and secondary benzylics. So secondary allylics and benzylics are more stable than regular old tertiary carbocations. And last in my loop here are my tertiary allylics and benzylics. Okay? So I only have representative allylics and benzylics up here. But this is now my new and improved carbocation stability series. Okay? And it's all about the resonance, man. All about the resonance. So note where to put in your primary, right? More stable than a secondary carbocation, but less stable than a regular old tertiary. And then at the very end come the secondary allylics and benzylics, and then the tertiary allylic and benzylics. Okay? So this is really important because SN1 and E1, we can change some of this up by adding in these allylics and benzylics. Okay? All right. So that's the first thing we need to do is be able to classify the alpha site in a greater way now, classify the alpha site. The second thing we need to do after we classify the alpha site, right, is to look at what nucleophile is being added here. That's really the next thing that we want to do. What is the nucleophile that's being added? Because the nucleophile that's being added is going to speak to the mechanism that is going to happen, right? So nucleophiles, I remind you, are categorized in a bunch of different ways, but mainly the pKa of their conjugate acids. So on a pKa scale here, I have things that have a pKa below 0, and these are what I would consider weak nucleophiles. Okay? There's one sort of category of, they sort of do lots of different things, but things down here are I minus, that's derived from HI, pKa minus 10, so this is down here. I have things like H2O, right? That's a weak nucleophile. Conjugate acid is H3O plus, pKa minus 1.7, right? So a bunch of weak nucleophiles. Weak nucleophiles have conjugate acids whose pKa's are below 0. This is where I find my weak nucleophiles. When I'm between 0 and 11, I have what I would consider a moderate nucleophile. And a moderate nucleophile is basically something that is charged, oftentimes charged, okay, and looking to react, but is sort of, it's stable enough on its own that it's going to look to react in not the fastest way, right? It's going to look to sort of for long-term stability, not just short-term stability, I guess, is one way to think about it. Things that belong in here are things like F minus, derived from HF, pKa 3.2, CN minus, derived from HCN, pKa 9, SH minus, derived from H2S, pKa 7, right? So there's a bunch of what I would consider moderate nucleophiles.
I just want to clarify, wouldn't the pKa of H2O was 15?
Okay, the pKa of H2O itself is 15.7, but if I classify on its conjugate acid, I first have to derive H3O plus, whose pKa is minus 1.7. This is very confusing. I totally agree. So remember, you look at your nucleophile, you make its conjugate acid, then you classify the pKa. Never classify the pKa of the nucleophile alone, right? There's only a few that would have pKa's, like waters and alcohols and amines. The rest of them, right, you would never, you look at something negative and you'd be like, I can't have a pKa, right? So that makes sense. Always on the conjugate acids pKa. Once I get above 11, I'm really in strong nucleophile category. And strong nucleophiles generally, if they can, okay, if they're set in a situation where they're going to behave best, they can act like a base. They're really reactive. They're looking to react fast. They're looking looking for short-term stability instead of long-term stability. So they're pulling protons. They're proton pullers because the first thing anything encounters is a proton when it attacks a molecule, right? Organic molecules are surrounded by protons. So if you're looking for fast reactions, the fastest thing you're going to be able to do is pull a proton instead of find your way into an alpha site or anything like that. So things up here include OH minus, conjugate acids, pK is 15.7, methoxide, right? That's up here, etc. Okay? So we classify them, we chunk it based on what we see. Okay? So when I classify the nucleophile, I might think charged and not charged. That might be one way I need to classify. But there might be times that I have to really hone in and more carefully classify. Okay? You know that SN2 reactions happen almost exclusively at primary sites. It's pretty much the only thing that's going to happen down there, right? So generally all charged nucleophiles, right, or pretty much all nucleophiles are going to run that SN2 reaction. Okay? When I'm up at tertiary sites, I know that I can have E2, SN1, or E1, and really that's also a charged, not charged distinction that allows me to understand what mechanism is going to happen. But when I'm at that secondary alpha site, I need to be very careful. Do I have a weak nucleophile? Do I have a moderate nucleophile? Or do I have a strong nucleophile? Because that matters. All mechanisms are possible at those secondary sites. Okay? All right. So let us do a few examples before I leave you to do the remainder of them. Actually, I think I'm going to leave these examples for you to do. These don't have any of those new special classifications in them. Okay? So we're going to do one site that does, okay, a few problems that do, and I'm going to put them up on the board, and we're going to practice what we think can happen. All right, let's start with these three. Okay, so I start by classifying the alpha site. So I think through these problems and I say, okay, the alpha site's right here, and this alpha site is secondary, and it's benzylic. Okay, so secondary benzylic now has a special meaning to me. I'm going to treat it like a tertiary site, right? In terms of carbocation, I'm treating it like a tertiary site, right? I've got to be very careful because a secondary benzylic carbocation is relatively stable, okay? It's relatively stable. So I've got to really think about that. Secondary benzylic, all right? So I know that it can do SN2, it can do E2, it can do SN1, it can do E1, all right? All of these are open and available for this special category. So I then go to the nucleophile. Remember to can all of your alkali earth metals, right? Or alkali metals because they have nothing to do with it, right? They're just the counterbalance to the charge on the nucleophile. So the nucleophile is OH minus. OH minus has a conjugate acid H2O whose pKa is 16, right? 15.7 or 16. So this is classified as a strong nucleophile, a base. At secondary site, this is going to behave as a base. This mechanism is an E2 mechanism. Doesn't matter that it's being run in water. The solvent just slows down the mechanism. The only time it's going to change the mechanism is if I have some weird nucleophiles whose properties can change when the solvent changes, and there's very few select ones of those. Okay? So this is an E2 mechanism. And this E2 mechanism, in essence, means that the OH minus is going to pull a proton from what we would say is the beta site. Remember, we always pull from the more substituted beta site unless I'm using, you all know? tert butoxide. That's exactly right. I always pull from the more substituted beta site unless I'm using tert butoxide. I pause. Good. So, now in this case, we see push out of the leaving group, and I get now this alkene as a result of my E2 reaction. Okay? We're going to see that. All right, problem number 2. I go right into the alpha site. Here's the alpha site. I classify my alpha site. So this alpha site is primary. It's also allylic. So this means it's like a secondary carbocation. That's what I want to think, right? It's like a secondary site, really, in terms of SN1, E1. All right? So I need to keep that in mind. All right. I look at CH3OH. I think, what is the conjugate acid of CH3OH? It's CH3OH2 plus, whose pKa is minus 2.4, right? First thing I need to do is make its conjugate acid. This is the conjugate acid of it, and its pKa is minus 2.4, which makes this a weak nucleophile. And a weak nucleophile at a primary allylic site is going to do an SN1 reaction. So this is going to run an SN1 reaction, proceeding through a carbocation intermediate. Okay? All right. I'm out to my third problem. I have an alpha site that I would classify as secondary. A secondary alpha site is really just like a secondary carbocation, very good carbocation, right, if I was to proceed through one. So I'm going to consider that as I move forward. I'm going to can the sodium and put a minus in front of that oxygen. That's my nucleophile. Secondary site can run SN2, it can run E2, right? It can also, because it's good carbocation, can run SN1 or E1. So my decision comes on the nucleophile. The nucleophile is derived from phenol, right? So phenol has got a pKa of 10, and hence, since its pKa is 10, I know this is a moderate nucleophile. And this is going to run an SN2 type mechanism. This is an SN2 type mechanism. Okay? So this is my product from that, focusing only on the regiochemistry. Okay? To fold in the stereochemistry, let's just review out loud. You guys always remember SN2. SN2 always comes with what type of stereochemistry?
Inverted.
Inversion. Inversion of the alpha site, right? Inversion means if my alpha site is R with a halogen on it, it will be S with the nucleophile that is being swapped out. Inversion of stereochemistry. What about SN1?
Either. Both.
Racemic, right? Because I proceed through a carbocation intermediate, I can get equal probability of R or S stereochemistry when I do SN1. And there is a stereochemical component to E2. Does anyone remember what it was? Zaitsev's rule is a regiochemistry piece, but absolutely, Zaitsev's rule is absolutely at play, right? That states that we always get the more substituted alkene from the reaction, which is why almost all bases are going to pull from the more substituted beta site, because that leads to the more substituted alkene. The only base that doesn't pull from the more substituted beta site is T-butoxide. That will always give me the less substituted. Does everyone remember? Oh, that's actually alcohol. So you guys learn about the Evelyn effect? No? Okay. Oh, sorry. We'll move on past that. My question, though, is what is the stereochemical piece to E2? Yeah?
The hydrogen acid from off-cancer.
That's exactly right. So it's anti-coplanar. So if you look at, say, the classic example for that is, I always think that's the eraser. That's not the eraser. Okay. The classic example for that is this one here. I will set up two E2 reactions. Each of these is E2 in nature. Okay? So to be E2 at these secondary sites, I need to be using a strong base. So I'll use sodium, I'll use S oxide here, I can use hydroxide here. These are each strong bases. Doesn't matter what the solvent is, so I'll just use their corresponding conjugate acids there. Okay? In this case, since the hydrogen on the beta site and the leaving group need to be anti to one another, right? That means that this here, this has the methyl anti on the more substituted beta site, right? The hydrogen is syn. You will not see E2 from here. You'll see E2 from the less substituted site, even though you're not using T-butoxide, because you are required stereochemically to have an anti-relationship between the beta hydrogen and the leaving group. So this leads to this alkene, whereas this is set up fine for an anti-reaction from the more substituted site. And so this leads to this piece here. This has further consequence if you are in a straight chain backbone, right? Because an RR stereoisomer would give you a different product, E or Z alkene, than an RS. Everyone remember that? So that was the consequence on straight chains. I can't see that really. That's a very difficult question, so I don't know if that'll pop back up. Yeah?
Shouldn't there still be a methyl group on the alpha?
Yes, there's still a method group. Thank you very much. Thank you. That's what it wasn't what I was focusing on, but yes, there is still a method group, so thank you very much. Yes?
How do you know OPH is modeling food?
So OPH is derived from phenol, right? Its conjugate acid is PHOH, and its pK is 10. So the pKa's really help you. And if you don't believe me yet, when we really get into 241 material, you'll believe me. You really need to know your pKa's, okay? We'll come back around on Friday and do some more substitution elimination as we move on to alcohols, ethers, and epoxides, okay?